Hello everyone, this is Kavita from the group Birds. Today our group will be discussing the topic of analysis of semi-volatile organic compounds by EPA 625.1 using SLE and tandem mass spectroscopy. The objective of this topic includes determination of SVOCs in industrial wastewater by SLE and tandem mass spectroscopy. We are going to cover this topic under the subtopics Introduction, Sample Preparation, Developing of SLE, and Analytical Methods. SVOCs are subgroups of VOCs that these likely to be liquids or solids at low temperature because of their high boiling point and high molecular weight. In second point, I have mentioned some examples for SVOCs, and here these are the health effects because of these are of high concern because of their high potential negative effects on humans. In this method, in this topic we are discussing the EPA method 625.1, which uses SLE, that is supported liquid extraction, and GCMSMS, which is also known as tandem mass spectroscopy. This EPA method this is updated method for EPA 625, where liquid extraction is used. The advantages of SLE over LLE is it requires minimal it requires minimal sample handling and yields significant productivity gain in the laboratory. It doesn't form any emulsions like liquid extraction. Here the analysis is done by GCMSMS, that is MRM mode. This MRM mode is able to select predefined ions for analysis based on M by Z ratio, that is mass and ionic ratio, hence its specificity is ensured. This flowchart will give information on how the samples are being prepared. Here matrix we have taken is industrial wastewater. Analytes include SVOCs. First step is sample pre-treatment. Under this, before sample extraction, it undergoes pre-treatment with water or pH adjusted buffer in 1:1 ratio. Next step is load. In this, add the aliquots onto SLE cartridge with the sorbent material natural silica under low vacuum for 2 to 5 seconds to initiate the flow. Here we have the waiting period for 5 minutes. In this period, sample gets absorbed onto sorbent and neutral analytes concentrate on the surface. Next step is elute. Apply extraction solvent MTBE, that is methyl terbutyl ether, approximately 5 times the volume of sample. Leave it to flow under gravity and apply low vacuum when the flow stops. Then analytes are then selectively eluted of the material using immiscible organic solvents. These eluted analytes are vacuum evaporated and reconstituted with the suitable solvents. These can be analyzed by GCMSMS, that is gas chromatography and tandem mass spectroscopy. This picture shows how simple the SLE workflow is. It is as easy as step 1, 2, 3. In step 1, we have to load the sample on SLE sorbent. In step 2, we have to give 5 minutes. In this period, it will sample gets absorbed onto solid support. And step 3, here we have to add extractant solvent. So analytes gets extracted into the solvent. This is the elution.
Hello everyone, this is Frida, and before continuing, I just wanted to reiterate the method summary, which Kavitha has already mentioned somewhat, as I will be covering some components later on in the presentation. So as you can see, the method consists of 5 steps, 2 sets of extractions followed by concentration, qualitative identification, and quantitative analysis. For this method, the matrix is industrial wastewater. Industrial wastewater is a complex matrix. It consists of multiple contaminants like solids, microorganisms, and heavy metals, to name a few. And although industrial wastewater is the main matrix for this method, additional potential matrices can be considered, such as sewage sludge or effluent water. So for this method, the analytes are the organic pollutants found within the industrial wastewater samples. The EPA does provide a list of the analytes that may be analyzed using this method. These target analytes are classified into 3 different tables, which you see on the side. Fortunately, the list is very, very long, so we will not get over it, but you should know there are different classifications for the analytes.
Hello everyone, I'm Nusrat Yasmin and I'm covering the middle part of our topic. So since the supported liquid extraction method is based on the same principle as the liquid extraction, but there are a lot of advantages of this method than the liquid extraction one. So I'm mostly covering on the advantages of this method. And at first I would like to tell about the supporting material which is working on this method, and that is diatomaceous earth, which is used as the support for the separation process. And this material occurs naturally and it is porous, chemically inert material with a high surface area. And these properties enable water to easily load by a capillary action onto the diatomaceous earth. And like the liquid extraction process, these have also the 2 liquid phases that interact with each other. Phase 1 is formed when the aqueous solution like water, plasma, serum, etc. is loaded and free to flow via capillary action for a period of time, and this enables the absorption of the water on the surface of the diatomaceous earth. And in this method, the need for shaking and manual extraction of the solvent layer are eliminated as a result of the efficient interactions via solvent flow. So this method can be easily automated by combining 96 well plates and robotic samplers that allow a great number of samples to be processed in a single day, and also enable higher throughput of the samples. So eventually it is better in terms of processing time than the liquid extraction process. Now here I want to introduce an amazing feature which is Camelot S, and it's for the supported liquid extraction, and it is an synthetic sorbent and it's very ideal for biological, food and environmental samples. For years the diatomaceous earth material has been used for the SLE extractions, but since diatomaceous earth is not manufactured and it's difficult to control particle size, which can compromise the results also. So Camelot is a synthetic extraction product which has a controlled particle size and delivers consistent flow and uniformity in every batch. And the SL extraction with Camelot S reduces the variability, improves matrix removal, and requires minimal extraction solvent, which leads to increased the analyte concentration. Now here I'm showing the development of the supported liquid extraction method, which is following several easy steps that save you hours or days of headaches down the road, as well as giving you the peace of mind that you are getting the best recoveries possible. So the left-sided picture, it is showing 16 steps that is required to thoroughly keep out the best sample pre-treatment as well as the best extraction solvent required for the most application. And the purpose of this sample pre-treatment is to promote partitioning of analytes into the organic phase. The charge on any acidic or basic group should be suppressed wherever it is possible, and this is particularly important for the polar analytes. And if when you are doing a panel of more than one drug type and want to find the overall optimal conditions for a single method, then this tactic can be a wonderful tool for you. So basically you are preparing for 4 wells, which is showing in the right side picture, that here preparing 4 oils with each pre-treatment solution, and you are using 4 different extraction solvents on each of the pre-treated sample, and this gives you a total of 16 samples which you can evaluate in parallel, and eventually it will save your time. So if you can evaluate now the recoveries by the chromatography or mass spectrometer to find out the method that provides the optimal result. Now my last slide is showing the performance of the supported liquid extraction method, where selected from our selected paper in the first phase of the work focused on the EPA method 625.1, the semi-volatile organic compounds, the classes of nitrosamines, pesticides, phenols, PHs, and PCBs in industrial discharges are analyzed. These fall into 2 categories of the BNA compounds, where the BNA compounds means basic, neutral, and acidic compounds. And here each group of the compounds was extracted separately. The acid fraction containing phenols was collected first, then followed by the base or neutral fraction containing PHs, PCBs, and so on. Then each fraction was analyzed separately, and here the boxes are showing the lowest and the highest range, which is from 70 to 130. So the average recoveries for these were found to be within this acceptable range, 70 to 130%, and the exception was only for the benzanthracene, which is about 67%. So these resulting extracts are analyzed finally using the GCMS method. Thank you.
So, as you saw in the method summary, the second to last step is the qualitative analysis of each sample. So, the identification of the analytes found within the sample is accomplished by the comparison of data from the analysis of the sample itself. So, the results for each analyte in each field sample should be reported, and the report should be specified if they are above or below the QC standards specified by the EPA, which you can find in the method itself. And for each analyte, you should calculate the recovery and the standard deviation from that percent recovery or the identification of the analyte. Finally, you should compare the results of the corresponding acceptance criteria, which is provided by the EPA, as you see here in Table 6. So each potential analyte does have a corresponding acceptance criteria. You should specify if the analyte found within your sample passes or surpasses the level specified by the EPA. Finally, the last step of the method is the quantitative analysis. So once your analyte has been identified, you should quantify the analyte based on the analyte's primary characteristics. The EPA does also provide a table which specifies each analyte's primary characteristic, as you see here on Table 4. And for your final report, you should not only include the primary characteristic, but also the retention time and the relative abundance of the characteristic masses for each analyte, as you see in Table 2 towards your right, and that should be included in your final report for your findings. So finally, you can present your results using a chromatogram, and a chromatogram is basically a graph that displays the separation of mixtures within a sample using chromatography. So in the chromatogram seen in this slide, you can see the separation of the semivolatiles or the analytes found within your sample. And that concludes our presentation. This slide includes our references. On behalf of Team Bird, thank you.